In the world of artificial intelligence, there's this one huge fundamental question that's kind of underneath everything else. How do we actually measure intelligence?
I mean, we see these incredible headlines all the time, right? AI systems like AlphaGo or OpenAI 5, they've achieved what you can only call superhuman performance in games like Go, StarCraft, and Dota 2. They are processing information and making moves at a level that is it's beyond what the best human experts on the entire planet can do. But this right here raises the multi-billion-dollar question. Achieving a super specific, very narrow skill is one thing, but does mastering a game, no matter how complex it is, actually equal genuine, flexible intelligence? The kind of intelligence that you and I have? Well, that's exactly what we're going to unpack.
To find the answer, we first have to understand a really common mistake in how we think about AI. Let's call it the skill versus intelligence trap. And believe me, it's a confusion that has shaped the AI field for decades.
Okay, so this breaks down the core difference. On one side, you've got task-specific skill. Think of this as the final product, the artifact, like a really good chess program. It's often brittle, meaning it completely breaks when it faces something it hasn't seen before, and it usually needs just a mind-boggling amount of data to work. But general intelligence, on the other hand, that's the process of learning itself. It's adaptable, it's flexible, and it learns efficiently without needing a whole universe of data.
And this is not a new problem, not at all. There's even a name for it, the AI effect. For years, as soon as we figured out how to make an AI do something complex, like play checkers, we'd immediately just dismiss it. We'd say, oh, well, that's not real thinking. We just keep moving the goalposts.
And here's where the confusion really sinks in. As humans, right, to master a game like chess, we use our general intelligence, the process, to go and acquire that skill. So when we see a human grandmaster, we correctly assume, wow, that person is intelligent. But an AI can get to that exact same skill level, the artifact, through a totally different path, often without any of that underlying general intelligence. We're mistaking the skilled program for the intelligent process that created it.
And crucially, developers can kind of buy this illusion of intelligence in two main ways. First, they can just hard-code all the knowledge and rules directly into the system. Or, and this is much more common today, they can just throw an absolutely astronomical amount of training data at a problem, basically letting the system brute force its way to a very, very specific solution.
And when I say astronomical, I really mean it. OpenAI's Dota 2 system, it trained on the equivalent of 45,000 years of human gameplay to beat the world champions. 45,000! And yet, when they released it to the public, regular players found new, creative strategies to beat it in just a few days. It had incredible skill, for sure, but it was brittle. It just wasn't truly adaptable. So, if measuring raw skill is the wrong approach, then what's the right one? Well, we have to redefine the true goal, and that leads us to a much more powerful and I think much more useful definition of intelligence.
Here it is. The new goal shouldn't be skill itself, but skill acquisition efficiency. In other words, how good is a system at learning? How quickly and efficiently can it take a limited amount of experience plus whatever it started with and generalize that into a useful new skill? That's the real measure of intelligence.
Imagine two different systems, and they both start with the same few data points. Those are the known situations. A system with higher intelligence can generalize from that very limited information to create a much, much larger operational area. It can handle a way wider range of new, unknown situations. It's all about the conversion ratio. How well do you turn information into capability?
A great analogy for this is just physical fitness. A truly fit person hasn't just trained to run one specific marathon on one specific day. They have a general capability, strong lungs, strong muscles, that lets them adapt to a ton of different challenges, whether that's running, swimming, or climbing. Intelligence is basically the cognitive equivalent of that general fitness.
So if humans are kind of the gold standard for efficient learning, it makes a lot of sense to look at our own starting point. How exactly do we do it so well?
For a really long time, there were these two competing ideas. One was that the mind is a blank slate, a tabula rasa, that learns everything from experience. The other idea was that it's just a collection of fixed, specialized programs that were built by evolution. Well, the modern view is actually a combination of the two. We're not blank slates. We're born with a foundational set of what's called core knowledge. And these built-in priors are the very source of our powerful ability to learn.
So what's in this starting code that we get?
Well, developmental psychology suggests it comes down to a few key systems. We seem to be born with an intuitive grasp of objects and basic physics, an understanding of other agents that have goals, a basic sense of numbers, and an innate concept of space and geometry. This is our evolutionary head start.
So, okay, if we're going to redefine intelligence as skill acquisition efficiency, and we anchor it in these human-like starting points, well then all of our old tests are basically obsolete. We need a completely new kind of IQ test for AI.
And that is where the Abstraction and Reasoning Corpus, or ARC, comes in. It's a benchmark that was designed from the ground up to measure exactly this kind of human-like general intelligence.
So how does it work? It's actually brilliantly simple. An AI is shown just a handful of example pairs, a before grid and an after grid. From just those few examples, it has to figure out the abstract rule that transforms one into the other. Then it has to apply that same abstract rule to solve a completely new test grid.
Now here's the key, the most important part. The tasks in ARC are completely novel. This makes it literally impossible for an AI to just memorize solutions or brute force its way through with a giant data set. It can't cram for the test. It has to show true, on-the-fly reasoning using just those few examples.
So let's bring this all together. What does this new perspective really mean for the future of AI? And more importantly, for its impact on our lives?
This right here perfectly summarizes the new framework. You see, intelligence isn't just one thing. It's a hierarchy. Down at the bottom, you've got the task-specific skills, and that's where most of today's AI operates. Above that are broader cognitive abilities, and then at the very top, you have general intelligence, the power to generalize and learn anything efficiently. And this isn't just academic talk. For the AI applications we really want, reliable self-driving cars, actually helpful domestic robots, genuinely smart personal assistants, we need systems that are flexible. The real world is messy. They have to be able to handle the unknown unknowns, not just perform a narrow skill in a controlled environment.
And so we arrive at the central message. The true goal of AI research isn't just to create better game players. It's to create better, more efficient, and more adaptable learners.
This leaves us with a final and pretty powerful thought. This whole line of research isn't just pushing us toward smarter tools, it's pushing us toward technology that can genuinely learn and adapt on its own. The question then becomes, what happens to our world when our machines can finally learn just as well as we can?